Okay, so section 5.1 will be projective space. Okay, and I'm going to jump straight ahead to the definition. If you read the notes, there's a bit of more sort of didactic stuff beforehand. But I want to jump straight in with the definition. So 5.1 projective space. So we define n-dimensional projective space denoted Pn, so blackboard P to the n, to be the set of lines through the origin of the affine space a to the n plus 1. So when you take just the set of lines, you really, can be made sense of, you end up dropping down a dimension. So an plus 1 goes to Pn. Right, so we need to be able to label the lines through projective space, and the way that we're going to do that is through a set of coordinates for projective space, which have a slightly different property from those in AN, we have to take coordinates in AN up to some equivalence, and the equivalence that we're going to take is by multiplication by any non-zero scalar. So given a point x1, sometimes people start with x0, but in these notes we're starting with x1, going up to xn plus 1. I should say, with not all x1 up to xn plus 1 equal to 0, so not the origin in AN, there is a unique line. There's a unique line through the origin and this point x. Okay, but there is not a unique choice for x to get that line. We can also multiply by any scalar. So for lambda not equal to 0, we get the same line from lambda times x. So we need to take the points in affine space up to this equivalence. And this is where the idea of homogeneous coordinates come from, which is where you get the colon notation that I was using earlier. So this is then definition 5.2. Homogeneous coordinates. So any n plus 1 tuple of numbers x is x1 up to xn plus 1 determines with x not equal to 0, so at least one of these things has to be non-zero, determines a point in Pn. the point is called a homogeneous, a set of homogeneous coordinates of n-dimensional projective space, and denoted x1 colon x2 colon colon up to xn plus 1. Where we get the same point if we multiply it by some non-zero scalar lambda. For lambda not equal to 0. Okay, let's do the most basic case, which is actually nice and easy to draw a picture of, as is done in the notes. So if we do, I'll go through example 5.3 and hopefully draw something for you. So when n is 1, we perform this this construction. We get what's called the projective line, and it's called the projective line because it's really is one-dimensional. So consider P1. Every point is a pair x colon y, where at least one of x and y is non-zero. So and you can, so there are basically, so projecting onto a an affine space, you can see that you get almost everything. So we're in A2 and we're looking at all the lines through the origin. So this is my y axis and this is my x axis. We can see what happens if we just take a projection through the line y equals 1. This is almost the idea of stereographic projection, but you're going to get a point on this line with one exception. So you get each line through the origin gives you exactly one point along the along this affine line, normal affine line, except for the one that's parallel to it. So along the line y is 0. So if y is non-zero in these coordinates here with xy, then you can divide by it because you can treat that as the scalar that we're allowed to multiply by. So then point xy is actually the same as the point x over y 1, right? Which is explaining why you get exactly 1 point on this line for every line that goes through the origin. So when y is 1, so you just get whatever this thing is. But you do miss 1 point. So, but we miss the line y equals 0. So just this, the x-axis in other words. Because then we can't divide by y in this way. But since we know that x has to be non-zero if y is 0, So x 0, and now we are allowed to divide by x because it can't be 0. So we get a single extra point. And what this extra point is referred to as is the point at infinity. So if you take the line y equals 1 plus infinity, then you get the projective line. So it's almost like a circle, but it has but where the circle, the end of the circle is actually infinity. Right, now in the notes I've just sort of described this. It gives a generalization of this idea, where you pick a coordinate, say the last one, say, well, what happens if that's non-zero? Well, then I can divide by it, and then I get a one-to-one correspondence with an affine plane, so of one dimension less than the ambient space. So if we're in A to the n plus 1, fixing one of the coordinates to be 1 will give you a hyperplane of one dimension less, so an. Which is exactly what we did here. We took a plane and then we projected to a line, which is obviously one dimension less. So you can do that, and the only thing that you have to then consider is what happens when, in fact, that last coordinate is 0, and then you get what are called points at infinity. So I'm not going to go through example 5.4 because it's basically the same content as the definition 5.5. So we're just going to jump straight into definition 5.5, which is an affine chart. So let Pn have homogeneous coordinates. Should say homogeneous coordinate system. x1 colon x2 colon up to xn plus 1. And then to each one of these coordinates, you get an affine chart. So we're thinking kind of like as if we were mapping out projective space. So you'll take, in the same way that you can't take the globe and sort of nicely squash it onto a piece of paper, you can take a part of it where you can do that, and you therefore get a sort of chart of part of the space that you're looking at. So it's coming from the idea of sort of nautical mapping. Okay, right, but to each coordinate xi, there is an associated affine chart, and we're going to denote it a sub I to the n, containing all projective points. So again, a projective point is a line actually in the ambient space a to the n plus 1. So there's going to be an affine chart that contains a subset of all those points with xi not equal to 0. Because if xi is not equal to 0, we can divide by it and then therefore treat it as 1. So it's going to be the set, so the set of points that we get here, ai to the n, are going to be equal to all those homogeneous sets of homogeneous coordinates in Pn, such that xi is not 0, and because we're now allowed to divide by xi because it's non-zero, we can actually just imagine that xi is 1. So go up to ui minus 1 and ui plus 1, and then all the way up to un plus 1. Okay, so these are all referred to as, with respect to this chart, these are all referred to as finite points, and the ones that are outside this chart, so the ones where xi is equal to 0, those are thought of as points at infinity. So with respect to ai to the n, so this particular chart, these are the finite points, and the remaining points which are in Pn but not in this chart, these are points at infinity. So points at infinity.